Look around, and the physical world appears continuous. You can move an object by a millimeter, smoothly and without interruption. But at the atomic scale, that continuity shatters into rigid, separated jumps. To understand where this discreteness comes from, we examine trapped particles. In 1993, IBM researchers demonstrated that these rigid levels manifest as physical structures in the laboratory. This is a scanning tunneling micrograph of their creation, a quantum carafe. The experimenters carefully arranged 48 iron atoms into a perfect circle on a flat copper surface. This ring acts as an impenetrable wall. Inside that boundary, the surface electrons are trapped. Notice the glowing concentric ripples of red and yellow filling the interior. These ripples represent standing waves of electron probability density. The bright crests map out where a trapped electron is most likely found. The experimenters only provided the iron boundary. The resulting pattern emerged on-radically because the electrons were confined. This suggests that quantization, the forming of discrete levels, might be a direct result of trapping a particle. To see if that is true, we have to look at the math that governs the trap. To prove the connection between confinement and discrete levels, we examine the simplest theoretical model, the one-dimensional infinite square well. We define a region from position 0 to a length L, where potential energy is 0. A particle inside experiences no forces. At the exact boundaries, 0 and L, the potential energy spikes to infinity. These are the walls of our well. Because the walls are infinitely high, the particle cannot penetrate them. The probability of finding it outside this box is 0. This establishes the physical trap. Now, we must apply the wave equation to see how the mathematics responds to these boundaries. The engine of our system is the time-independent Schrödinger equation. It determines which wave functions, psi, are permitted to exist. Inside the box, potential energy V is 0, so that term drops out. We are left with a wave equation for a free particle. But the walls impose a strict constraint. A wave function must be continuous. It cannot jump instantly to 0. Therefore, exactly at the left wall, the wave function must be 0. The same logic applies to the right wall, reaching 0 at position L. This geometric restriction is identical to a vibrating guitar string. It sustains frequencies that perfectly fit between its fixed anchor points, specifically whole integers of half wavelengths. If a fractional wave attempts to form, it cannot vanish at both fixed endpoints simultaneously. It contradicts the physical anchors and dampens out. The electron follows this same geometric constraint, representing a wave of abstract probability amplitude. If a probability wave attempts to hit the right wall at a non-zero value, it violates the boundary condition, and the mathematics rejects the solution. The Schrödinger equation allows a continuous range of solutions, but the box itself filters them. Only a specific, discrete set of spatial modes can perfectly fit these boundaries. Because only exact half wavelengths fit, the wave number k is restricted to discrete steps, integer multiples of pi divided by the box length L. For a free wave, energy is equal to h bar squared times k squared over twice the mass. Substituting our restricted wave number into this formula reveals the allowed energy levels. The critical variable here is n, the integer representing the number of half wavelengths. Because n is squared, it dictates exactly how the energy levels will scale. This chart plots those calculated states inside our infinite square well. At the bottom is the ground state, where n equals 1. This is the lowest possible energy a confined particle can have. For the first excited state, n equals 2. Because 2 squared is 4, this level sits exactly 4 times higher than the ground state. The next state, where n equals 3, sits 9 times higher. Notice the gaps between these rungs. As n increases, the distance between energy levels physically widens. We have arrived at the proof. By simply placing walls around a particle, a continuous spectrum of energy is shattered into an expanding discrete ladder. Quantization is the mathematical consequence of confinement. Since this system involves a wave trapped in a box, a student naturally assumes the particle is physically vibrating or bouncing back and forth. The time-dependent wave function proves this assumption is incorrect. To advance a single energy state through time, we multiply the spatial wave by a complex exponential phase. This phase term acts as a clock, rotating in the complex plane as time passes. The speed of this rotation is governed by the energy level. A higher energy state rotates faster. But we only observe the absolute square of the wave function, the probability density. When you square a complex exponential, it multiplies by its conjugate. These terms perfectly cancel each other out, and the clock is removed from the equation. The resulting probability density is motionless. The curve remains frozen in place regardless of how much time passes. This confirms that an energy eigenstate is a stationary state. If the universe only existed in these individual modes, nothing would ever move. If single states are frozen, how does classical motion, like a wave packet bouncing between walls, actually emerge? The answer is superposition. We combine different energy states, so the particle exists as a mathematical mixture. In this mixed state, we have the ground state, E1, and the first excited state, E2. Because these states possess different energies, their internal phase clocks rotate at different speeds. The angle between them constantly shifts. When we calculate the observable probability density, we must square the entire mixture. This generates a mathematical crossterm. This crossterm does not cancel. It creates an interference pattern that beats at a frequency equal to the exact difference between the two energy levels. This beating crossterm physically sloshes the probability mass from the left wall to the right wall. Spatial confinement builds the rigid, frozen energy ladder. But it is the superposition of those distinct rungs that breathes dynamic motion into the physical world.